Bismillahirrahmanirrahim. Assalamu alaikum. This is our 22nd lecture of Formal Methods for Software Engineering, and I am Fakhr Lodhi discussing with you algebraic specifications. In the last lecture, we started to discuss algebraic specifications. Algebraic specifications are used to specify abstract data types and interfaces. We shall be talking more about that later. So the notation or the structure that we saw last time, we said that in the algebraic specification, we have the notation that we are using. We had 5 components. The first 2 components known as the introduction, where you specify the name of the specification and name of the sort for which we are writing the specification. Sort is the type or an abstract data type that we are writing the specification for. And we may also include things such as import and so on and so forth. What are the other specifications that we are using inside this specification? Then we describe the behavior of the abstract data type, the operations supported by this abstract data type, give an informal specification or informal description of the methods or the functions supported by the abstract data type. Then we give the signature, and signature is kind of the header. It gives us the input parameters, the type of the input parameters, and the output value or type of the output value. So for all the methods, we write the signature. That is, these are the parameters that it takes, and this is what it produces. Just like our header file in our C or C++. Then finally, we write axioms. In order to write axioms, the basic rule of thumb is that we first of all analyze the methods or the functions supported by the type. And we can categorize these methods into 2 types. One is called constructors. The other one is called inspectors. Constructors are all those methods that create the object or change the state of the object of that type. And inspectors are all those functions which give you some result without actually changing the state of the object. So these are kind of queries. So we have constructors and we have inspectors. So what we do is we write axioms, we specify the behavior or we give the semantics of the operations by writing axioms for each inspector in terms of the constructors. For each one of the inspectors, we write axioms, and the input to that inspector will be the constructor. So the rule of thumb is that if we have n inspectors and m constructors, the total number of axioms that we will write is n multiplied by m. But this is the general rule. This is not always true. Last time we saw the example of an array, and we wrote the specification for an array. And in that example, we used this particular rule and we wrote 6 axioms. What we are saying here is when we write these axioms, since the input parameter to an inspector is the object itself, so what we say is that if we apply a function that changes the state of the object and then we inspect the value, what should we get? So once again, since for each inspector, one of the input parameters is the object itself. So you always apply the inspector on an object or an instance of that type. So what we are saying is, we say by applying a constructor, we change the state of the object. So when we change the state of the object and then we make this query, so we have a number of inspectors and each inspector gives us a certain value back. It is some query which gives us some aspect of the object back. So we say, okay, we apply this particular function which modified or updated the state of the object. Now we check what happened. What was the modification? So we apply each one of the inspectors onto the modified object and we write what should we get, what is the expected result. Like I said, that in most cases, what we do is we write inspectors in terms of constructors. But in some cases, there are other things that we need to look at, and we may have to write these axioms slightly differently. Today, we shall start with an example where, that rule of thumb is not applied. It is slightly modified. And we shall see why did we have to modify that rule, or why did we have to apply a different principle here. And, what do we get as a result? So here is the example of a classic example of a stack. So we have a stack abstract data type. Once again, it can take an element, and we also have an undefined of this type. So we say, when we get an undefined, that is also of this type. This is the sort stack, and in this particular case, we are not importing anything. We are simply using or writing the specification for this abstract data type stack. Once again, I am not showing anything in the informal part, but we have these 5 methods, the 5 functions that are supported by this sort stack. The first method is create. It creates a stack, and in this particular case, it does not take any parameter as input. So, what we are saying is we are creating an unbounded stack. The stack is not bounded here. So it will create a stack which is not bounded. There is no upper limit specified for that. We have the push operation. It takes the stack and an element, so it puts this element on top of the stack. And since it does that, so we have created this stack with the help of this create function. We put a new element on the stack. That means we change the state of the stack. There is something new to the stack, and hence we get a modified, updated stack. The pop function takes the stack and gives us a modified stack after chopping the top element from the stack. It is not giving us the top element, but it is just chopping the top element. So this is a slightly different definition of pop function, but here there is a purpose that I wanted to only write it like this. I'm only saying that it returns only one value here. It is not returning 2 values. So in this particular case, if I wanted to get a value back also, that is the top element back, it would return the stack, that is the modified version of the stack, updated version of the stack, where the state of the stack has been changed, and the top element also. So at this time, I'm not complicating things. So I'm saying that it chops the head off, takes the top element, and gives me the rest of the stack back. The top function once again takes the stack and it gives me the top element of the stack. And this is empty function takes the stack and it gives me a Boolean value back. It basically checks whether the stack is empty or not, and it gives me a true or false. So these are the 5 methods that I have for my stack. Now, for these 5 methods, we have create, which creates a new stack. We have push, which modifies the state of the stack by putting one more element on top of the stack. We have pop, which takes the top element, throws it away, and gives me the rest of the stack back. And I have is empty function, which tells me whether the stack is empty or not. And I have the top function, which gives me the top element of the stack. So these are the 5 methods. So normally when we write the abstract data type for a stack, this top and pop, they are combined together in this pop function, where you modify the state of the stack and also the return the top element of the stack. But in this particular case, I have written 2 separate functions so that I did not have to introduce a new concept how to give you more than one value back. So once again, other than that, there is nothing special about it. Another very interesting or important thing here is, for simplicity here only, that at this point in time, I do not want to deal with certain types of errors at this point in time. Although we will be talking about that, we will be discussing that later on, how to handle that kind of situation. But here, I do not want to tackle or write specifications to handle certain types of errors. So what I do is, I say that when I try to pop from an empty stack, there is no error. What I get back is I get an empty stack. If the stack is empty, I try to pop it, since there is nothing, it gives me the empty stack back. So this is another slight deviation from the normal operation of the stack abstract data type. But, the rest is what we used to have in our stack. Now, there are 3 methods, that is create, push, and pop, that update the state of the stack. And there are 2 methods, that is top and is empty, that do not change the state of the stack, that gives you some value back. So we have 3 constructors and we have 2 inspectors. 3 constructors and 2 inspectors. So what we will do is, we will try to write axioms for the 2 inspectors in terms of the 3 constructors. So the total number of axioms in this particular case will be 2 multiplied by 3, and we will have 6 axioms. So let us try to write these axioms for this particular sort, that is the stack, the way we are defining it. So let us do that. So we have the 3 constructors. We have create, we have push, and we have pop. The 2 inspectors that we have top and we have is empty. So let us take this is empty, because it is, relatively speaking, easier to just give the specification for that, at least for some of these, maybe not for all. So let us write. So we say is empty create and what is the answer? When we have just created the stack and we check if the stack is empty, the answer ought to be yes, true. So that is what we get. So we write and when we say is empty, the other operation is push. It takes a stack and an element that we are pushing on top of the stack. Now in this particular case, what happens? We took the stack S and we have added, or we have pushed one element on top of the stack. Now the question is, if we ask this question, make this query, is the stack empty? The answer is obviously no. We have just added one element to the stack and hence it cannot be empty. So we write false here. So far, so good. Very simple, straightforward thing. Now, here is a more interesting case. We have is empty pop what is the answer here? Now, this is a very interesting case. We have a stack and we have popped one element from the stack. Now the question is, if I ask, after popping, is the stack empty? What do you say? Now, it all depends. If there were more than one elements in the stack is not going to be empty after this pop operation. And if there is only one element, if there was only one element before the pop operation, so after this pop, there is nothing in the stack, and hence the stack will be empty. Now the question is, how do we write it? It can be either true or false, depending upon what was the previous situation. So, we have a problem at hand. So let us just keep it like that. Let us think about it, and we'll come back to it later. So I'll just keep it open that at this point in time, I do not know the answer. Let us try to write this for other, the axioms for top, and then see what happens. So let us write this top operation and axioms for top. So we have this top. So we have this top here, and we are trying to write the axiom with respect to create. Now, create means that we have just created a new stack. So when we have just created a new stack, what is there? There is nothing. The stack is empty. And if the stack is empty, if we try to look at the top element, if we ask this question, what is at the top of the stack? Obviously, it is undefined. There is nothing. So what we say, when we try to get the top element from an empty stack, the answer is undefined. It is an error. So we write this. Let us now write the top push stack S, the element E. So what we have done here is we have just added one element onto the stack. So that element, we all know, this is a stack, it goes at the top. So after adding that element, if I make this query, okay, tell me what is at the top, obviously the element at the top is the element that we have just pushed. So the answer is E. And finally, we once again have this top once again a very interesting question. Okay, we have a stack. We did the pop operation. So we chopped off the top of the stack. Now what do we have at the top of the stack now? Do we have any clue? It is the second last element that we had in the previous stack. But what is that element? How can we specify? How do we state that this is the value that we will get? Once again, we have a problem and we cannot solve this problem. So what do? We saw that this pop here and the pop here, in both these cases, we could not determine the answer. We could not determine whether the stack would be empty after the pop or not. We could not determine the element after we have popped the top element. So we could not determine the top element there. So we have to find some alternatives. So what we do is, when we are stuck, when we cannot find an answer, what we do is we take this pop, the operation for which we cannot find the answer, and we use it, or we try to write axioms for that operation in terms of other operations. That is, what we will do is we will treat this pop just like the other inspectors, and we will write the axioms for pop in terms of create and push. So this is what we are going to do. That is, we will write axioms in terms of create and push, the axioms for pop, and see whether we can find an answer to these questions. So let us try to do that. So what we do is we have this pop, create, so when we have a new stack, create, we try to pop some element from this stack. What do we get? As I told you earlier, as I mentioned earlier, that for simplicity, because I did not want to deal with certain types of errors at this point in time, I simply say when I try to pop from an empty stack, I simply get an empty stack. I do not get anything else. So what we do is we get this create. Since this create gives me an empty stack, so this is what I get. So very simple. Once again, if I try to pop from an empty stack, I get an empty stack back. I do not, get anything else. So this is, the first operation. Can I state anything? Can I specify pop in terms of push? Let us try that. So we have this pop. So I had this stack S. I added E on top of that stack. So I got a new stack. Can the state of that stack change? If I pop, what do I get? If I pop, what happens is I will chop the top element. And what was at the top element? The element that I just pushed. So what happens? If I chop that element, I'm left with the old stack, that is S. So I get this S. So what happens in this particular case? What we have done and what we have said here is that in certain cases, we may not be able to write axioms for certain constructors. And then what we do is we try to take that constructor and try to write axiom for that constructor in terms of other constructors. अच्छा, यहाँ पर एक चीज जरा इंटरेस्टिंग और इम्पोर्टेंट है टू नोट that if we look at pop and push, one is a primary constructor. You cannot pop before you can push. You cannot pop before you had pushed something. That is, push will have to be applied before you can pop the element. This is the order. So you can create a stack with the help of push operation, but you cannot create a stack. You cannot modify the stack, a newly created stack, with just the pop operation. So push जो है वो फंडामेंटल ऑपरेशन है. पॉप हालांकि एक मॉडिफायर है और कंस्ट्रक्टर है, लेकिन वो पुश की तरह फंडामेंटल नहीं है कि जब आपने एक नया स्टैक बनाया उसकी स्टेट आप चेंज नहीं कर सकते बाय सिंपली अप्लाइंग द पॉप फंक्शन. Whereas on a new stack you can push elements and then that will change the state of the stack. So push is a primary operation and pop is not a primary operation from that point of view. So we also try to look at the primary operations. So the primary operations will remain as the constructors, but the secondary operations could actually, be treated as kind of inspectors, although it is not an inspector, but we write the specification of that in terms of the other constructor. So once again, what we are trying to do here is, what we are saying is, we are specifying the behavior of this of inspectors in terms of the constructors. We say we apply this constructor that changes the state of the object. Now we make a query. So what do we get? What is the answer in terms of that query? And that is what this specification is all about. So once again, the number of axioms roughly, or as a rule of thumb, is going to be n multiplied by m, where m is your inspectors and m is your constructors. But if you change in this particular case, the number did not change, but in some cases it could change. But you have to write one axiom for each inspector for taking each constructor one at a time. So that is the number of axioms that you will have to write. Next, we look at another famous example, and that is the example of a list. In the case of a list, the abstract data type that we are going to define here or specify here is what you will find in the Lisp programming language. Lisp, as you know, or as you probably know, Lisp is a programming language where everything is treated as a list. So we apply operations on lists, and then we can create and add elements, and we can remove elements from the list, and do certain functions on the list. So this list is a very, very similar abstract data type that we find there. And with the help of this example, we shall see certain concepts that we did not see earlier. So what is, once again, let us look at the basic definition, the basic axioms, and then the basic signature of the list, and I'll give you the informal specification for that, and then we will write the axioms for this abstract data type, that is list. So in this particular case, the slight variation is going to be where you will see that we are going to apply recursion here. So in certain cases, the specification is going to be recursive. How is that? Let us first look at the signature, and then we will write the axioms. So here is the specification for list. Once again, the first two introduction part. Here are the functions or the signature. Once again, we have this create, which creates a list. Then we have this cons function. This cons function is used to create a list. So what it does is that you take the list and you add an element to that list. It gives you a new list, and this cons adds this element to the end of the list. So adds an element to the tail. This tail function chops the head of the list off and gives you the remainder of the list. So if we had 5 elements in the list, it will take the first element from the list and give you the rest of the list back. And the head method gives you the element at the head of the list. And the length method gives you the length of the list. Now we have these functions. There were 5 methods that we saw here. The create, which creates a new empty list. Cons, which adds one element to the end of the list. The tail, which chops the head off and gives the rest of the list. And in this particular case, if the list, the input list is empty, it gives an empty list back. Then it gives the head, which gives you the top element of the list. And the last method that we had was the length, that would give you the length of the list. So we have to write the axioms for this abstract data type. Once again, there are 3 constructors because there are 3 methods through which you modify the state of the list. That is create, which basically creates, cons, which adds a new element to the list, and tail, which chops one element, the top element, and gives you the rest of the list. And there are 2 inspectors. that is head, which gives you the top element of the list, and length, which gives you the length of the list. So once again, let us write the axioms for those. So we have cons, we have tail, we have create, on the other hand, we have head, and we have length. So let us write the axiom for length, because this is a very simple case. We say length of a new list that we have just created length of a new list is 0. Obviously, there is no element there. Length of cons list L element E, adding one more element to this list E, is equal to, now we have this list L, we have added one more element to this list. So what is the length of the new list? Length of the new list is one more than the length of the old list. So we are giving a recursive definition here. So we say it is equal to length of L plus 1, whatever that was. So if that was initially empty, we have one element. If it had two elements, we now have three elements, and so on and so forth. And length of tail now once again, this is an interesting question. हम शायद ये सोच रहे हो कि जब टेल ली है तो हम what we have done is we have reduced this size by 1. So it should be the length of the old list minus 1. Unfortunately, the answer is not that simple. What happens if the old list is empty? If the old list is empty, we will get an empty list back. Otherwise, we get this, the length of the old list minus 1 back. So what we do is we say if L is equal to create, then we get 0. Otherwise, we get length of old list minus 1. So in this particular case, we have the if clause here. So very simple, straightforward thing. Nothing very complicated. Now let us look at the head. So let us try to write axioms for head. Head of create we have just created a new list. There is nothing in that list. So when we try to get the top element from that list, what do we get? Once again, it is the same kind of a problem that we had with the stack. So what we get is an undefined or an error condition. So we write an undefined. The value is undefined. It is an error condition. What happens when we try to use cons? List L, element E. Now, in this particular case, what happens when you add an element with cons? The element is added at the end. So, if I take the head of this new list, what do I get? If the list was initially empty, now I add one element, there is only one element now. So that means, if I take the head of this list, that is the element that I will get. Otherwise, if the list was not empty and I take the element at the head, what do I get? This element was added at the end, not at the head. So what happened was I will get whatever was at the head of the original list. So this is what I'm going to write. So if L is equal to create, I get E back, else I get head of L. And finally, let us write this head of tail. What do I get? Head of tail. I take this list L, I chop the top element. This is what the tail operation gives me. I chop the top element and I am given the rest of the list. So what is at the head of the rest of the list? This is the same problem that we had with our stack. We don't know. So we are stuck. So once again, what we will do is we will have to, use the same method. That is, we will take this now head as a non-primitive operation and then, write the axioms for head in terms of the other constructors, that is create and cons. And then we shall see what happens. So, we have to write the axioms for tail, for in terms of create, so what is the tail of a new list? An empty list. What do we have? When we chop the head off, what do we get? The answer is, like I said earlier, in this particular case, you will get an empty list. So the answer is create itself. Now the second question is tail of cons. What do I get? This is a very interesting question. I have this list L. I added one element to this list, and that was added towards the end. And now I chop the top element and I want to get the answer. What is the answer to this particular problem? How can I specify this thing? Add मैंने पीछे किया है, chop मैं इस साइड से कर रहा हूं, and I want the answer कि ये मुझे इसके बाद क्या चीज मिलेगी. Now here is the recursive definition once again, and this is a very interesting recursive definition. Please pay attention. What happens? Let's say अगर आप इसको पहले चॉप कर दें and then add one element to it. So let us look at this example. So let me show you. Let us assume that we have this list. This is L. We add one element. So this is, let's assume that this is 1, 2, and 3. Data is here. So we add one element 4 to this list. So we say cons L4. So we will get this new list 1, 2, 3, 4 here. And we say tail of this list. So this element will be chopped, and this is what we will get back. Now, we start with this list again. We say tail of L. When we say tail of L, we will get this list here. And now we add four to this list. That means we will add this element here. So that means if you look at this thing, this and this, they are the same. So what we do is we say this is the same as adding 1 after chopping the head. So chopping the head of this newly created list, the answer is the same as if you chopped the head of the old list and then added E to that list from which you have already chopped this head. So cons and tail and cons, they are defined and specified in terms of each other recursively. Very interesting, but sometimes you have to do it like that. But once again, see how precisely it specifies the behavior of all these different operations. So what we do here is, once again, we analyze the signature and we identify the constructors and the inspectors. The constructors and the inspectors are identified. And what we try to do is we try to write axioms for all the inspectors in terms of all the constructors. But sometimes we cannot do that. So in that particular case, what we do is we take a step back and we look at the situation. Where are we stuck? We identify those points where we are stuck. We identify that operation, and then we kind of take it as an inspector and then try to write the axioms for that function in terms of the other constructors, the remaining constructors, and see if we can complete our job. And axioms can be written in many different ways. And recursion in this particular case is a very useful tool that we can use to specify our different operations. So here, with the help of these examples, previously with the help of stack, we saw how can we convert this convert this constructor into an inspector and then write the axioms for that constructors in terms of other constructors and then solve the problem. And in the case of this list, we looked at this example and saw how can we use recursion to specify the behavior of different data types, abstract data types. So these are our tools and it will come very handy with us. So today we have seen a few examples of abstract data types, and we have seen how to write algebraic specifications for these abstract data types. This algebraic specification, as I mentioned earlier when we started to discuss algebraic specification, can be used to specify the entire system. And especially in the context of object-oriented methodology, what we have seen is there is this concept of reusability. We have seen some reusability. We can import the other specifications and use those specifications. But here in algebraic specifications, we can also reuse the previously defined specifications. We can extend those specifications. And when we extend those specifications, we do not have to rewrite the whole thing again. It is just like inheriting from the superclass and making a subclass. So in the next lecture, we shall be looking at those examples and see how can we actually enrich and extend already written specifications. And then, later on, we shall see how can we specify a large system using these specifications. Until then, मुझे इजाज़त दीजिए. खुदा हाफिज़ और अस्सलाम वालेकुम.